Hey everyone, Mr. C here. So today we're going to talk about the Atwood machine. So today's objectives. We're going to prove that the acceleration of the entire system in the Atwood machine is the same. So the Atwood machine we're going to learn is a pulley machine. We're going to learn that both pieces are going to accelerate with the same magnitude. We're going to derive a formula to describe the acceleration of the objects in the Atwood machine, and then we're going to solve a sample Atwood machine problem. So here's an example of an Atwood machine. We have two weights, in this case a sumo wrestler and a baby, connected by a rope, we're going to assume massless, and it's strung over a pulley. Notice that the sumo wrestler has a weight component, m2g, so we denote his mass by m2, and the baby has a weight component, which we denote by m1g for the baby's mass times the acceleration due to gravity. We also note that we have these arrows pointing up, which is labeled F of t, and that represents the tension in the cord. One of the things to think about as far as tension is, since this cord is taut, meaning it's not going to bend or have any slack in it, we know that the tension on this side of the cord is going to be exactly the same as the tension on this side of the cord. So we know the force of tension on one side equals the force of tension on the other side. All right, so let's go ahead and simplify the problem, and then we'll start. All right, so here's our simplified Atwood machine. We see we have, two masses, M1 and M2, connected by a pulley, and we're going to assume that M2 is larger than M1. So what that means is when we let go of this system, we would expect M2 to go down and M1 to go up. So the first thing we need to do is draw a free body diagram of both pieces, and then just to get an idea of what's happening. So let's start with M2. So for the free body diagram for M2, we have its weight vector going down, which is M2g, and we have a tension going up, F of t. For M1, we have a weight vector going down, which is M1g, and then again we have its tension going up. So we'll label that force of tension. Okay, now what we're going to do is we're going to apply Newton's second law to both pieces to try to figure out what's going on here. So, starting with the first piece, we see the sum of the forces on one equals the force of tension minus m1g, because it's going in the opposite direction, and we see that equals the mass of block 1 times the acceleration of block 1. Then for 2, the sum of the forces on 2, we see that's equal to the force of tension minus m2g, because again, it's going down opposite of the tension, and that's equal to the mass of 2 times the acceleration of 2. Now what I want to do is I want to go back up and look at the Atwood machine. What I know is if this string's taut, I know that if M2 is pulling down, it's going to pull M1 up. Also, if it's taut, you know at the rate that M2 is going down should equal the rate that M1 is going up. So from this kind of just thinking about it, we kind of get the idea that the acceleration of 2 going down should be the same in magnitude as the acceleration of 1, but they should be in opposite directions. So if we say that M1 is going to accelerate up, then we should say M2 is going down. So what I'm going to do is I'm going to say A2 equals negative A1. So now let's go back down here. What I want to do is I want to solve for the force of tension in both pieces, because what did I say earlier? The force of tension is going to be equal for both sides. So for system 1, we have force of tension equals M1 A1 plus M1G. Then for system 2, write this one in blue, we have force of tension equals M2, and now remember I said that A2 is equal to negative A1, so I'm going to write negative A1 here, plus M2G. Now, since the force of tension is equal for both of them, I can set these two equations equal to each other. So let's go ahead and do that. All right, here we are. So we have M1 A1 plus M1G equals M2G minus M2A1. So this is M2 right here. Okay, now what I want to do is I want to put the A's on one side and all the G's on the other side. So doing that, I get M1 A1 plus M2A1 equals M2G minus M1G. Now I'm going to go ahead and I'm going to factor out my A1s and my G's, and I find that A1 times the mass of 1 plus the mass of 2 equals G times the mass of 2 minus the mass of 1. And now I can go ahead and I can solve for A1, because again, remember we were trying to solve for the acceleration of the system. And I'll find that A1, when I divide it all out, is G times M2 minus M1 divided by M1 plus M2. And there it is. We've solved for the acceleration of the Atwood machine. Just to note, a little food for thought, what would happen if the masses were the same? What would be the acceleration? Well, now we're going to prove it. So, if we say M2 equals M1, let's go ahead and plug that into our equation and see what happens. Well, A1 equals G times M2 minus, I'm going to plug in M2 for here also because M2 equals M1 over M2 plus M2. And what do I find that equals? Well, the M2's cancel out and that becomes a 0. So now I have G times 0 divided by M2 plus M2. Well, that whole thing just ends up being 0. So we see when the masses are equal on that machine that the acceleration is 0. Well, let's do another one. Let's say that M2 is much, much bigger than M1. Let's say, for just an example, M2 equals 1,000 kilograms. And let's just say that M1 equals basically 0 kilograms. So it's almost weightless. Well, let's try to find the acceleration of the system for this problem. So I'll go ahead and I'll plug it in my equation, and I'll say A1 equals G times M2, which is 1,000 kilograms, minus 0, that's M1, divided by M2, which is 1,000 kilograms, plus M1, which is 0. And what do I get? I get G times 1,000 divided by 1,000, and look at that. We get an acceleration of G. So the Atwood machine makes perfect sense because if the masses are equal, we see we get an acceleration of 0. And if we have one mass that's really heavy and one mass that's basically nothing at all, that's basically just like an object free falling. And if an object's free falling, it should free fall at the acceleration due to gravity. And we just showed that yes, it does fall to the acceleration due to gravity, G. All right, thanks a lot. Hope this helped you guys.